Hello, student. And here is the guidelines for the lecture for today. We're going to cover the last two sections in chapter 21st. And we're going to move to the chapter 22nd, talking about the electrical, or the current, sorry. And we end up with the just two sections in the chapter 21st. So the first one, what I'm gonna start with just as a connection between electric field and the eco potential or electric potential lines, how to find the relations. To draw the electrical field line based in the eco potential lines or vice versa, so you need to keep in your mind just two main facts. So the first fact here, all the time, electrical field is perpendicular to the equipotential line. All the time, electrical field, it should be perpendicular to that line. All the time. The second fact, you have to keep it in your mind, electric field point is or the in the direction of decrease of electrical or electric potential, which means all the time to identify the direction of electrical field, I am just looking for where the electric potential value decreasing. So the decreasing electrical potential, that the way to identify the direction of electrical field. If we wanted to draw that situation here, when we have equal potential value minus 10, minus 5, minus 2, we apply those two concepts, perpendiculars, and they are in decrease of electrical field. So I have this line supposed to be go this way, and I have go this way here, and all the time toward the decrease, and it should be perpendicular for the one intersection with those lines. So similarly with that case. So the only thing you're gonna be, because this one decrease the electric potentials in that way, and it should be perpendicular for all the eco point or the eco line of electrical or electric potential. Here is the similarity for that one. We have the positive and negative charge, and here is the equipotential value. From the positive, here is the from the large value 10, 8, 6 until 2. And here is the negative charge from minus 10 to the 2. And in the middle between those two charges, the electric potentials equal 0. That's why sometimes we call equilibrium point or equilibrium line. Okay, where is the electric potential equal 0. So one thing you need to keep it in your mind, the electrical field, when it is the equipotential, they are very close to each other, that the magnitude of electrical field, it is large. When the distance between equipotential, it is large, that's where the electric field is less. As a direction, so we mentioned it should be goes that way. That way. What the direction? The direction should be in the direction of decrease equipotential, decrease of the equipotentials. The same thing, direction decrease of the equipotentials, and even for negative charge, the same thing. So we can draw any line of electrical field based in those two facts. Okay. And all those lines should be perpendicular with the equipotential line. Those two factors, two key point to find the relation between the electric potential and electrical field. Let's play with some numbers here right now. So here is we have electrical potential or equipotential line from 20 volt to the 0 volt. And we know that the direction of electrical field in the direction of the decrease of the equipotential. So this is the directions. And we know it's gonna be perpendiculars. And we know the value of electrical field will be decreased when the difference of the volt decrease. So that's the formula that we're gonna find, or we can use it to draw or to calculate electric field at any certain distance. Okay, so what we need from that distance, we need the locations, and we need the equipotential value. So here is we have 2 points. One of them, they are located between the equipotential 10 volt and uh, 30 volt. Second equipotentials, second point located between 10 and minus 10. Let's call this one is B, and we call this one is A, and we try to find the electrical potential in those 2 points. So basically, straightforward formula, delta V divided by D. So we need to find what the delta V is. Here is the 30 minus 10 will be 20 volt divided by, I have the distance, 1 centimeters, which basically 0.01 meters. We end up with this one, 2000 volt per meter. The second one here, I have even my estimations before I start. I expected to see the electrical field in that point will be less because the difference will be the increase, and even the distance will be large. So we're gonna use the same formula. Here is the delta V divided by D. I have my delta V 10 minus 10 will be 20 volt divided by the D, it should be 0.2 meters. So we end up with this one, 1000 volt per meter. So expected to see less value than the dot at point A. So that's to confirm our fact. And here's the very interesting problem here. The interesting problem here, in that case, what we are given, we are given the electrical field with 500 volt per meter or Newton per coulombs, and we are given 3 points, dot A, dot P, dot C. And they ask you to find the potential difference. You don't know how the potential difference line or the equipotentials line located, or how you can draw it. So the key point here, using the two facts that we mentioned previously, we can identify the equipotential line of electrical potential. So here I have the directions here, two facts. One fact, the electrical field, the equipotential, it should be perpendicular. That's perpendicular one. Okay. That's the two line here. The second fact, we're gonna reverse the fact. The direction of electrical field mean the direction of the decrease of equipotential. So this is the second one, this third one, and we know right now this one should be larger than this one, larger than this one. This one, the increase, this direction is here, decrease V, just to keep it in your mind that case. So let's throw one line in that case, just in purpose to solve this problem here. Now, we know the formula that's related between the electric potential and electrical field. So I have E from previous slide, delta V divided by D, and I have E and I have D. I'm looking for delta V. So delta V from here equal E times D. So that's the formula that I will use. So here the difference potential will be increased with the increasing B. Okay. Now let's find that. Let's see the difference of the D for the E and A and P. They are located at the same equipotential. So from here, A and B, they are both of them, they are equal. And both of them should be larger than C. Okay. That's the equipotential value. So the A and B, they are equal since they are located in one equipotential value. And C here, because in the toward the electric field, the directions, the equipotential should be decreased. Now to find the delta VAB between A and B, it should be equal 0. since they are located in 1 volt, on 1 ecovolt. Okay, so this one I can find is immediately 0. Now I need to find the voltage difference between A and C. A and C, what I'm looking for, here is the A, here is the C. So my interesting point is just the distance. So I have E, it's 500 volt per meters, times D, 0.015 meters. So I end up with the 7.5 volt that value. Regarding for the delta VBC, the same concept. I have E 500 volt per meters times, I'm looking for the B and C. The distance, they have the same distance between A and C. So times 0.015 meters, and those units cancel to each other. I end up with the value 7.5 volt. The same value that we got last from the previous one. Okay, so that's what we have. How to find that the electrical or the equipotential line value when we are given electrical field directions. Okay, so the next part of our second video, we're gonna discuss some information regarding for the two plates they are connected together to find the capacitors and energy in the capacitor. At the end of this video, guys, and thank you. See you in next video.